Okay. Uh, Good morning here. We've got section 3.2 as today's lesson. It is on linear functions. We started our new unit on graphing things with functions. That would have been on Wednesday for us. Now we're talking about a particular kind of function. I should say a particular kind of equation. Here we start with the linear function or the linear equation. Right, and so at the beginning of this lesson, we're going to talk about three different ways we can identify a linear function. So number one is that its equation can be written as y is equal to mx plus b. And usually you'll see it written with the lowercase b. I'll do an uppercase just so we don't confuse it with a 6. But we say every linear function can be written with an equation, something like this. And we'll be doing a project later that will ask us to do this kind of thing. We'll have to make an equation, and this will be the subject of a couple of our lessons later in chapter 3. But for now, we kind of just have to know this one, and we'll talk about this in a second here. Right, m and b are just constants. Another feature of the linear function is its graph is just a line. If a function is not linear, then it's not going to look like a line. And then the last big thing here is that a linear function has a constant rate of change. Right? So we say that as I go from one output to the next, the change between the two is the same every time. And usually we're adding or subtracting the same number. We're not multiplying. We're not looking for multiplication. So in this example, example one, we're saying, do these things represent a linear function or a nonlinear function? And we got to explain. So number one, this would be a good example of a nonlinear function. And the explanation there is because it is not a graph. Not a graph, excuse me. It is not a line. We got that curve to it. This is actually called the parabola. Maybe you guys knew that from whatever math you took last year. And actually, we know what this kind of function is, and that'll be like what you study in Integrated 2 as sophomores. But for now, we don't really need to worry about it. What we are concerned about is this one in example B, right? This is a linear function. Its graph is a straight line here, right? It is a line. This is what we're looking for, is that it's got this kind of straight relationship. You might think, oh, it's got a slope like that. And really the other thing has a slope as well, but it's not a constant slope, right? We need to have a constant rate of change. And that's a question more for calculus. So if you're thinking, what am I talking about? Maybe talk to me your senior year. Here, right, we've got another way of representing a function in a table. We looked at this on Wednesday. And so what I'm looking at here is, okay, if the change between these two things is constant, here it is. I go +3 to get to this one. This is another +3 to get to that one. Another +3 to get to this one. That's good. Then this change should also be the same. And maybe you can see the pattern here, right? But as I go from one of the outputs to the next one, what we're doing is -6. And getting to the next one, we have another -6. Again, the last one, another -6. So because this is constant, we say that this is a linear function. So again, because the amount that I'm changing as I change inputs, the difference in the outputs is a constant number, right? So we say there is a constant rate of change. This is one of our big three things for identifying a linear function is the rate of change. And again, we're only looking for quantities that are added or subtracted. If I'm like multiplying everything by -6 here, then that would be not linear because the amount that each output is changing by the distance between them on a number line is changing as I go. All right, so maybe you could take a second and think about this one here. I can pause it, see if you can work ahead of me. Right, but as I go here, change 2 plus 2 plus 2. Okay, so the difference in the x values, that's constant. We only are curious about the difference in the y values. So here I have +7. Uh-oh, here I have +11. And then at the very end, I have +15, right? And so the difference between these is +4 +4 +4, right? So the rate of change of the rate of change is different. And again, that's a calculus question. We're only concerned about what these numbers are. And so because they're not the same, We say that this is non-linear. Right? So let me erase this. So this is going to be non-linear then. I would say that's because it is not a constant, which means level or even or flat rate of change. Great. And so on the next page here, we're just going to kind of summarize things. So I've got this table, right? In one column, I'm going to list the features of a linear function. In the other column, I'm going to list the features of a nonlinear function. So a linear function's graph is a line. A nonlinear function's graph is not a line. You'll notice the nonlinear function column is going to be very negative. Here, a linear function's rate of change is constant. A nonlinear function's rate of change is not constant, right? I kind of just have to negate that and say it's not what the linear one is. So for me, the linear equation is going to be y is equal to mx plus b. I can write all of them this way. The tricky part is finding out what is m and what is b. Those are just going to be numbers there. The x and the y, those stay the same. Those stay as variables. In the same way, uh, we could say that this is not going to be y is equal to mx plus b. I just didn't my period 3 point out, oh, couldn't we just like draw a little cross through the equal sign there to say that's what the equation would be like? Yes, yes, that would work just fine, right? But we're not looking for things like that. So here we've got 5 examples of equations, and we're saying, do they represent linear functions or do they not? So for me, right, this first one does, right? I'll say, yes, this is a linear function, right? But how? The key for me in proving that this represents a linear function is finding some numbers that are equal to m and b in this equation here. Right, this is big, and this will be what we do in a couple sections here. Y is equal to mx plus b. Here, right, because I kind of know where this is going, and this comes with practice, I can say if m is 0, and b is 3.8, I can make this equation. Y is equal to 0, right? That's my m, times x plus b, which is 3.8, right? Why is this equivalent? Maybe pause and take a second to think about that, right? But if I do 0 times x, that's nothing. So this whole thing is nothing. Nothing plus 3.8 is 3.8. So on this whole side, all I have is 3.8. So y is equal to that. And that's exactly what I have here. Right, again, this is a little tricky. I think there's a couple problems like that on your homework on big ideas, but you don't really need to worry about that a whole bunch for now. Again, this will be the subject of a couple lessons. Moving on to this next example, y is equal to root x, square root x, or radical x. We would say, no, this is not a linear function. We do not want no square roots allowed. Let me take a second to think about this. Is this a linear function? Again, no. No exponents. Right? Linear functions are very simple. We're allowed to have 2 different numbers, an m and a b, and then an x. Oh, this one's a tricky one. Is this a linear function? Yes, right? How do I get there? All right, I got to figure out what m and b are. If I can identify this m and b in this equation here, I can say it's a linear function, right? Many of you might have seen right away, we can distribute that 6. So 6 times x gets me 6x. 6 times -1 gets me -6. So m then is 6, and b is -6. I have to kind of switch this sign here. I take this whole thing. Here I had positive 3.8, so that was 3.8. Here I've got -6, so that's -6. This one follows the same pattern as before. No, we're not allowed to have exponents. I might even put an exclamation point here, but exclamation point. Boom. No, no exponents. Right, exponent stuff will be what you do in integrated 1 and integrated, it should be integrated 2 and integrated 3. All right, so here's just a little summary of stuff that we've done, and I'm going to mention this graph in a moment here, right? But in words, you can represent a linear function like an output is 3 more than the input. The equation there we've got y is equal to x plus 3, right? Maybe you could do an exercise. M here is maybe a little more difficult to see. Do. And it's just 1, right? Because it's mx. How many x's do I have? How many things am I multiplying by x? 1. I've got 1x. B is 3. And then we can represent a function in all three of these ways. So with an input-output table, with a mapping diagram, with a graph. And the graph is going to be the most important thing for us, kind of the easiest to interpret in a lot of times because we can get the most information from it. And here's how. We'll say that a solution to a linear equation in two variables, right? So the two variables being x and y is the ordered pair x and y. Everything that we did in Unit 1 required us to get a solution that was just one number, right? It was just x, or maybe it was m was the variable we were finding, or k, or something like that. Now we need two numbers to make up a solution, right? And here, what we'll do is we'll test some points. We'll say, are the ordered pair solution to this equation? So for all these points, I'm going to be referencing this equation. Y is equal to negative 2x plus 7. Right? In my ordered pair, the first number is x, the second number is y. So if I have y is equal to, my y is 1, then I'll have 1 is equal to negative 2 times x. So negative 2 times 3, right? If I put it in parentheses here, this is like times 3 plus 7. Right? These were the directions of the function. Take your x, multiply by 2, add 7, and you should get y. I'm given stuff for x and y, so now I just have to make sure that the right side simplifies. I'm only simplifying this side. Negative 6 plus 7, right? Oh, what's going on here? And then I add these two, I get just 1. Right, so we say yes, this is a solution. 1, 3 is a solution. Notice I'm using a and not the. They're going to be multiple. I'll talk about that in just a second. Now we could check this one right here. My x is 1 and my y is 3. So if y is 3, I'll have 3 on the left side times, or excuse me, is equal to negative 2 times 1 plus 7 on the right side. I got to simplify the right side. Negative 2 plus 7, that gets me 5, right? 3 is not equal to 5, so this point is not a solution. No, it is not a solution to that equation. All right, maybe you could pause this and do the last one on your own. Right, but again, we'd plug in 3 for y. Get negative 2 times 5. It's pretty poorly written 5 there, so I'm going to rewrite that. There we go, 5 plus 7. Simplifying only the right side, right? Because I got this left side already as simple as it can get. I get negative 10 plus 7. So you get 3 is equal to negative 3. And the answer is no. I know that's not a solution. Right, again, so what I said earlier was that you could have many solutions, and how can we visualize them with the graph? So here, all of these points on this line represent a solution to this equation that I had over here. So this y is equal to x plus 3. We're saying that any of the solutions, any of the xy pairs that'll make this equation true can be found on this graph here. And so maybe let's focus on this point. All right, maybe take a second, identify what this point is. All right, if you're reading the graph closely, you'll see that x is 1, y is 4. And so maybe I'll plug these in here. If y is 4, my function says take your x, my 1, plus 3, and you'll get your output. That's true, right? So here we've shown that this is a solution to that equation, and I could do the same thing checking this one. 2 plus 3, 2 is my x, is going to be equal to 5, right? I could check all of these. So the graph tells you where all of your solutions are. It's a big takeaway, and again, that'll be the subject of a lot of our later sections here. So I'm on to the next page now, right? Can I just mention that the graph shows all the solutions there? This is a big catch, though, for the domain, right? Remember, the domain is the set of all x values that the inputs can be. And here, we're saying that sometimes they're going to be distinct points, and other times they're going to be connected, right? Before, in our section 3.1, we had a graph of dots versus a graph that was a line. We talked about the domain differently. A discrete domain is only going to have certain numbers, and I'd encourage you to underline that as well, right? And so look at this picture, right? The discrete domain is just comprised of these series of dots, 1, 2, 3, 4, 5. A continuous domain is going to have all the numbers in an interval. Notice I've got a dot at 1, I've got a dot at 3, and then this whole thing is shaded in between the two, saying that I could pick values that are in between the whole numbers. I could have 1 and a half. I could have 2 and a fourth. I could have 3 and 3/8 or something like that. I could have a fractional amount here. In the discrete domain, I could have no of the values between the points exactly. I can't do 1.5 in the discrete domain. And so we're going to look at two examples of both, and I hope you're kind of connecting the dots here, and not literally, metaphorically, I guess, because you can only connect them for a continuous domain. But here I'm looking at the function y is equal to 1595x, right? This represents the cost y in dollars of x tickets for a museum. We're given this condition at the end too. Each customer can buy a maximum of 4 tickets. And so at this point in class, I'd ask you to figure out what is the domain, right? Again, the domain is all the possible values of x, right? So x is the tickets, the number of tickets that you can buy. And notice I'm using the word you can buy. You have the option to buy. 4 is the maximum. So a lot of people might have said, oh, the domain is 4. That's one of the values in the domain, right? What are the other possible values of tickets I could buy? 4 is the maximum. I could also buy 3, buy 2, I could buy 1, I could buy 0. I can buy any ticket. Say I don't like going to the museum. I don't buy any tickets at all. And now this question, right? Is the domain discrete or continuous? Here's how you can answer that question. Think, can you buy a partial ticket? Can you buy half of a ticket? Can you buy a quarter of a ticket? I'm not talking about can you buy like a child's ticket or something like that. I'm talking about can you buy one half of a ticket? You should get pretty quickly. No, the answer is no. You cannot buy a partial ticket. Because the answer to this question is no, because you can't have any of the values between the ones that you already found in your domain, we say this is a discrete domain. The domain only contains those 5 numbers, nothing in between them, nothing past them, nothing before them. And we're going to graph this then using a table. All right, so I know what the domain is. 0, 1, 2, 3, and 4. I can get the range or the y functions, or the y values or the outputs by following my function's directions, right? So my function is up here. The output is given by 15.95 times x. And I should have had these written down next to me, but I kind of remember them from yesterday. So I'll do 0 times 15.95, and I'll get 0. So my first point in my function is the ordered pair 0, 0. All right, so maybe I'll throw that on my graph right away. The next point, I do 15.95 times 1. So that's 15.95. Right, again, I get the ordered pair 1, comma 15.95. And I can throw that on my graph, right? I don't have to be super precise, but somewhere between 10 and 20, I get that second dot. 2 times 15.95, right? That's my direction. Take the input, multiply by this number here. I get 31.9. I'm pretty sure. Please check me on that, right? If I'm making mistakes here, fill it in with the right values there, but I think that's the right one we want. So then at 2, my y value is 31.9, which is somewhere like right around there. Then I do 3. This is where my mind gets a little foggy on this, but I'm pretty sure that's 47.85. And again, you can use your calculator to check to 3 times 1595, and you should get this, I hope, if I'm remembering right. All right, so then graphing this, I'll go 3 and then almost to 50, or not quite, almost to 50, maybe somewhere like right there. And then my last one, 4 times this 1595, I think we get 63.80. $63.80. So that would be the highest possible value I would pay for 4 tickets, my maximum that I could buy. Right, and so that one gets placed up here, 4, and then I go up to 63, which maybe is like right there. Right, and so my question for you to answer is, do I connect these dots or not? Maybe you've been quick to say, no, don't connect them, right? Discrete domains mean do not connect the dots, right? Why? The graph shows you the solutions of your equation or your function. Here, we already said I can't take a value between 0 and 1. that is not a choice for my domain, right? So I can't represent its solution on the graph at a point between the two dots, right? So the dots are the only things in my function here. So we'll say that's kind of it for us, right? We had to identify the domain first. Okay, our last example, and maybe you should take a little bit of a break here before I talk about the linear project that you're going to be working on, is this. A cereal bar contains 130 calories. The number of C calories consumed is a function of B, the number of bars eaten. So the first question is, does the situation represent a linear function? At this point in my lesson the other day, one of my period three, people were shouting out what kind of domain it was. We'll take that for part B here, but here I'm saying, does this represent a linear function? And this is the question that you'll be asked to answer on the linear project. And there's three ways we can identify a linear function, right? We talked about by looking at its graph, which we don't have yet. We talked about its equation, which we haven't set up yet, but we could if we wanted to. And we talked about its rate of change. That's the easiest way to identify usually if we don't know the other two things. So I'll get this here. So here, right, I can identify that this situation has a constant rate of change. Right, you might be thinking, what is it? Well, you can read the prompt here, right? So I'm thinking, how much does C change with every bar, cereal bar that I eat here? I'm reading the prompt. You can see that uh, the rate of change is 130 calories, C, per bar that you eat, per B. So because the amount of calories increases at a constant rate for the number of bars that I eat, then we say that this is a linear function. And so that is the task that you'll have to do in the linear project, right? Is figure out a situation where, okay, is the rate changing as I add one of something? Does it go up the same amount all the time? People were trying to do stock market in my other class. That does not work, right? That does not change in a linear fashion. B, find the domain of this function. Is the domain discrete or continuous? Okay, maybe the second question is easier to answer. Is this domain discrete or continuous? And so then think to yourself again, can you eat half of a cereal bar or a quarter of a cereal bar or even just a bite, however much a bite of a cereal bar is? The answer is yes. So this is continuous, right? And so maybe my explanation here is exactly that. You can have only part of a cereal bar. So because you can have a fractional amount between the whole numbers there, between the integers, we say that that is going to be a continuous domain. And so my last question is find the domain of the function, right? What are the possible values that I could have, right? So I'm trying to answer for my inputs for B, the number of cereal bars eaten. What is the possible number of cereal bars that I could eat? You know, I had some people thinking about this saying 130. No, that has nothing to do with the number of cereal bars that I can eat. That only tells me the number of calories. We're going to say that the number of cereal bars is definitely going to be something, right, in this window. It's going to be B is greater than or equal to 0. I could choose to have no cereal bars, but then maybe I eat an infinite amount. I eat cereal bars for the rest of my life. Maybe not a great dieting strategy, right? But this is a possibility for us. And I could have only half of a cereal bar, like we said here, or I could have three and 5/7 or something like that. I don't really know how you'd measure it, right? But in theory, you could get a smaller and smaller piece of the cereal bar. And so we'd say that this is good for our domain. I could have anything greater than 0. And so since I have a continuous domain, I think the big idea is math. It'll only require you to graph 2 points. And so I might pick two that are kind of spread out. So I'll say, what is going on with the value of B? C, whenever B is equal to 0, right, I'll get myself at the origin and I'll get myself at 2 here. And you could use 1 or you could use 3 or you could use any number that you want here. You could use any two numbers that you want as long as they're in the domain. Right here I've got that 0 is definitely in the domain, right? Because B is equal to 0 here. B is also greater than 0, so I chose 2. I would go ahead and say, how many calories do I get from consuming 0 cereal bars? 0 times 130 gives me 0, right? So here's my first point. And this is what Pearson will be like. It'll say array, which is a kind of a mathematical object where you have one end is a point and the other end is an arrow. For me, how many calories do I consume if I've had two cereal bars? So 2 times 130, that's me 260. Big ideas only wants you to do this. Place one point at the beginning of your array, place another point somewhere along where the array is. Right, and I could do another point if I really wanted to, right? If I consumed four cereal bars, and again, I'm just making up these numbers, 4 times 130 gives you 520. I could place that other dot way out here. For big ideas, they only need to do two. Where does it start? And then what is just one point that it goes through? And I draw that arrow saying that it goes on forever, right? Because I could pick any value from my domain, any value B, way out this way forever. That would be good there. And then again, why did I connect the line? Because it is continuous, because I can have points in between the whole numbers here. So continuous means connect the dots. Okay, and that is it, basically for this, right? We've got this last example, example six, but maybe take a break for a moment, right? And before you and a partner, and you must work with just one partner. There is no group of four, no group of five, nothing. Everybody has to be in a group of two. There's going to be one group of three since we have an odd number of people in the class, but the group of three knows who they are. So, right, if you haven't gotten an email from me about that, then you don't need to think about it. There's one group of three, and they'll be working together. And so if you don't have the paper in front of you, I'd go ahead and grab that now. And you want to write down the name of you and your partner. I only need one per group, one per partner set. I've got a couple extras there, but I only need one per partner pair. And so what you're going to be doing is figuring out situations in real life that can be modeled by linear things. And I'll talk about that briefly in just a second. But for now, we can go ahead and look at this example, right? And if you want to take a break before watching the rest of this, that's okay with me. But the prompt here is write a real life problem that fits the data in each graph, right? Is the domain of each discrete or continuous? I think you guys might be able to get the second part of that question pretty easily, right? Is this discrete or continuous? I've only got the dots here. There's no line between them. So we say that is discrete. In the same way, is this discrete or continuous? You have only got the line here, no dots, no dots. So this is continuous. Everything is filled in the interval. And so now we have to figure out a situation that would make sense. We have to identify independent and dependent variables that would make sense for the data here, right? So maybe I'll point out this one. This one's saying that if my input is 0, then my output is 6. If my input is 1, then my output is 5. If my input is 2, my output is 4, so on and so forth until I get to 0. If my input is 6, I have no outputs. There's 0 output. This one works the same kind of way. It's just a continuous thing, so we need to find a continuous set of data. So maybe see if you can think about this for a second. See if you can find two variables that work. Right, again, we'll be doing two variables, x, the independent variable, and y, the dependent variable. X, the independent variable, and y, the dependent variable. And again, I need two different situations, one where one's continuous and one where one's discrete. I was really liking this example from my other classes. I think my period 3 did this one. They said that, okay, if my x variable is the number of hot dogs sold, so put yourself in a concession stand seller's position here. X is going to be hot dogs sold. So as I sell hot dogs, as I sell one hot dog, two hot dog, what is this output? What would this be? Right? It's not going to be money made, right? Why would I be losing money for selling hot dogs? Maybe you've got some weird hot dogs. I don't know. The more intuitive thing here is if I sell one hot dog, then I've got 5 hot dogs left in stock. So I could say, Y is hot dogs in stock. Right? As I sell them, I'll have less in the store, the supply, until eventually I have none. If for some reason I only had 6 hot dogs on hand, maybe I'm throwing a barbecue for a group of close friends or something like that. And so if I had 6 hot dogs and I made all of them, I'd have none left. And these are discrete because in theory, I'm not going to sell a half hot dog or I'm not going to give someone a quarter of a hot dog or something like that. On the other hand, I'll keep rolling with this hot dog example. I've got this continuous data here. Maybe I'll do this, right? If I have hot dogs eaten, right? I could eat half of a hot dog if I really wanted to. If I have hot dogs eaten here, then Y would be hot dogs remaining. Say I bought six of them, right? I'm that person in the first example that bought six hot dogs. Then I eat them kind of one by one, and as I'm eating them, the amount is going down. That's fine. Right? Some people I think maybe even talked about maybe X is gallons of gasoline used, and Y is gallons of gasoline left in the tank. But notice the difference between these two variables, right? Hot dogs all the way around. This one is a discrete situation. This one is a continuous situation. Okay, for the linear project, again, you're working in a pair. You and a partner are going to be kind of figuring out three different situations, right? So for me, this could be situation one, this could be situation two. It doesn't matter if it's discrete or continuous, but you have to have some creativity here, right? You cannot use these two examples. I would say try to avoid food in your examples for topics one, two, and three. I gave you a tip, maybe think about time or think about units or something like that. That'd be a good thing for your independent variable. And I'm just going to do a quick sketch of what the chart looks like. So right here, I'll say this is like topic one. This should be what the piece of paper in front of you looks like. You've got the independent variable. I'm gonna say that's the ivy. And you guys, you don't really need to be writing this down. You should have this printed out in front of you. The independent variable, the dependent variable. I think here we've got the rationale, right? So this is how I know that my situation is linear. And then the source. And so maybe you'll have to do some Googling here to figure out certain piece of information, right? But I'll look at this. So mine is easy, right? And this is kind of why I want you to avoid this because it is so easy. I'll use my first example in that one that we just did, right? So my independent variable is hot dogs sold, right? Because as I sell hot dogs, right, I can change this amount. It is going to affect, the dependent variable is going to be hot dogs in stock. What's the rationale? How did I know this was linear, right? There's a constant rate of change. I'd abbreviate that ROC, right? One sold related to one, negative one out of stock. Say I had a deal going on where I did, you get buy one, get one or something like that. Maybe I'd sell one hot dog and then I had a minus two out of stock or something like that. Tell me about the rate of change here. I want to know what the rate of change is for your topic. And then the source, well, this was just a brainstorm. I didn't have to do any kind of clever thing there. I did have groups of people who were looking up information on Google to find out about the rate of change of things. There's a lot of examples to be had in sports. Like if I run a certain amount of miles, I'll lose a certain amount of weight or burn a certain amount of calories. Maybe look up on the internet, Google just how many calories or weight you'll lose for running a certain amount of miles, right? That is, I think, what another group did in my period three. Right, and so then I'd have to repeat this process for a different situation in topic two and a different situation in topic three. And then on the back, give me a quick summary of your three topics, and then I'm going to pick which topic you're going to do your report on. Right, big thing to be aware of here is this is just day one of the linear project. The linear project will be 4 days. There'll be a fourth day in a couple weeks here, I think two weeks to be exact. And this whole project is worth 10% of your semester grade. So this is a big deal. So take this seriously. Really put some work into finding your topics, right? It took some of the groups in my last class period 25, 30 minutes to do all three of these, right? Be sure the relationship is constant, right? If all three of your topics are kind of not linear, you'll not be allowed to do any of the three of them. I'll have you do this again. That would be a bummer. If you guys don't really do this with creativity, right? So if you're being like, oh, that group's doing this thing, so we'll do that thing as well, I'll also ask you to redo it, right? You should be kind of thinking creatively here, getting some interesting topics for all three of them. Again, this is due at the end of the class period, and then you have homework on big ideas. So I'll write that here just so you kind of see what I'm talking about, right? Maybe you're watching this at 2 times speed. Big ideas, homework. That is going to be due on Tuesday, so you have a couple days to complete that. This linear project day one, that's due at the end of the class period. Again, you get to pick your partners, and there should only be one group of three, and the group of three knows who they are. So everybody else finds someone to buddy up with. You got the papers there, right? They're not hole punched, so you turn those in. The papers that are hole punched, keep those. Those are your notes. If you have any questions, please let me know. And I think other than that, we're good here. So enjoy what's going on with everything on Friday. I hope the play was enjoyable. But other than that, I think you guys have everything that you need. Have a great one.